Alright, now let's look at problem number 2. While exploring a sunken ocean liner, the principal researcher found the absolute pressure on the robot observation submarine at the level of the ship to be about 413 atmospheres. The density of seawater is 1,025 kilograms per cubic meter. So we're supposed to calculate the gauge pressure on the sunken ocean liner, the depth of the ocean liner, the magnitude of the force due to the water on a viewing port of the submarine at this depth if the viewing port has a surface area of 0.0100 square meters. So we've got the surface of the water, and we've got a boat sitting at a certain depth on the sea floor, and you've got the little submarine. We'll call that depth D. We know that the density of the water given by the problem is 1,025 kilograms per cubic meter, and we also know that the pressure on the robot submarine here, so the pressure, the absolute pressure, is going to be 413 atmospheres. Right, and so part A of the question is asking for the gauge pressure. This one is very easy. It's just basically, do you understand the definition of gauge pressure? We know that the gauge pressure is equal to the absolute pressure minus 1 atmospheric pressure. The absolute pressure is going to be 413 atmospheres minus 1 atmosphere, and we've got the gauge pressure at this ship to be 412 atmospheres. And it's important to notice that this is a very simple calculation, but AP, this is a 2-point part of the question, and AP would only give you 1 point if all you put was 412 atmospheres. You need to show 413 minus 1, you need to show this definition, something that shows that you subtracted 1 from 413 to get 412. You can't just put the answer with no work. Part B is asking us to calculate the depth of the sunken ocean liner. We come in and we need to know that the definition of the absolute pressure here is the density of the water times the gravitational acceleration times some depth. You can call it H. In this case, actually, we'll go ahead and call that rho g d because the problem asks for the depth, capital D. So this is a very simple, so if I'm taking P equals rho g d, to solve for D, I get the pressure over the density times gravity. Now, here I do not want to put 413 atmospheres. I need to remember that 1 atmosphere is given in our constants sheet. It says 1 atmospheric pressure. 1 atmosphere is 1 times 10 to the 5th pascals. So, because we're using scientific 1 atmosphere, we got to make sure we take 1 atmosphere, turn it into 1 times 10 to the 5th pascals. So all we do here is we're going to take the pressure and we'll make our substitution as 413 times 10 to the 5th pascals divided by the density of water, which is 1,025 kilograms per meter cubed, times gravitational acceleration, which is 9.8 meters per second squared, and I'm left with a depth of, if I do the math correctly, it's going to be 4,111.5 meters. Remember the rule 2 to 4? So I'm going to go ahead and say the depth is 4,111 meters. That will be the depth of this ship, which is pretty deep, 4 kilometers under the surface of the water. Now, let's see what this is asking us to do next. It says, okay, calculate the magnitude F of the force due to the water on a viewing port of the submarine at this depth if the viewing port has a surface area of 0.100 meters squared. What is the force on a window of this little submarine if the window has an area of 00 square meters? Now, this is again, I know that pressure equals force over area, so force is going to be pressure times area, and I can take this and I can say, okay, I remember my pressure, which I calculated here, to be 412 atmosphere, 413 times 10 to the 5th. Remember, we're working with those units again, so 413 times 10 to the 15th. Pascals times the area of the window, which is 0.0100 square meters, and I'm given a force. That calculation is not too bad. It's going to be 4.13 times 10 to the 5th. Sorry, this is a 5th right here. Newtons. So 4.13 times 10 to the 5th newtons of force on that window. Very simple calculation, but be very methodical as you show your work. Now, let's see what the problem's asking us to do in part D. It takes this area and changes it a little bit. Suppose that the ocean liner came to rest at the surface of the ocean before it started to sink. Due to the resistance of the seawater, the sinking liner has then reached a terminal velocity of 10 meters per second after falling for 30 seconds. So it reaches a terminal velocity of 10 meters per second after falling for 30 seconds. D asks us to determine, D asks us to determine the magnitude of the average acceleration. I love seeing the word average. It's going to simplify the calculations. Average acceleration of the ocean liner during this period of time. Well, do not overthink this one. If this ocean liner starts to sink, all right, then I know that for part D here, I know that acceleration is defined as the change in velocity over change in time. We read that it reaches a velocity of 10 meters per second after 30 seconds, which means the change in velocity is from 0 to 10, which is a positive 10 meters per second. The change in time is 30 seconds. So my acceleration is 1/3 of a second, which is approximately 0.33, meters per second squared, which is 0.33 meters per second squared. That is the acceleration in this situation. For part E, it says, assuming the acceleration was constant, calculate the distance below the surface at which the ocean liner reached this terminal velocity. Well, not too bad. Same thing, except now let's say, okay, I've got my acceleration. Determine the distance below the surface. If you remember this kinematics equation, x equals your initial position plus your velocity component plus your acceleration component. I know that x minus x naught is going to be my initial velocity times time plus 1/2 at squared. So there's my delta x, my change in position that I'm looking for, or distance. I know my initial velocity is going to be 0, so my change in position is 1/2 times the acceleration times the time squared. If I'm looking for the total distance it's traveled, I know that my acceleration I just calculated to be 0.33 meters per second squared. I know the time was 30 seconds, so I'll make sure to square that. And so my change in position is going to be, if I do my calculations correctly, 148.5 meters. And I will, because it asked for determine the distance D, I'll actually take that and I'll say, okay, so the distance D is 148.5 meters. I doubt they would take off a point on that in the AP exam, but you will want to put, it asks for D, so let's go ahead and indicate it as D. Last but not least, calculate the time it took the ocean liner to sink from the surface to the bottom of the ocean. So this one's not too bad. Remember, you've got some distance below the surface. Let's go ahead for part F. You know that this ocean liner sunk below the surface. You know that this distance right here, it took 30 seconds to go 148.5 meters. So there's 30 seconds. And then there's going to be the rest of the distance, which the depth that we calculated before was 4,111 meters. So I know that the total depth here is going to be, get organized here, The total depth is going to be 4,111 meters. I took care of 148.5 meters as it accelerates. Now the rest of this distance is going to be 4,111 minus 148.5, which is 3,963 meters. And remember, the terminal velocity is 10 meters per second. So if I'm trying to find the time, I know that velocity is distance over time. So time is just going to be distance over velocity. Because it's a constant velocity, it's not changing. I don't have to take into account my acceleration here. So the total distance traveled is going to be 3,963 meters. The velocity is traveling at 10 meters per second. Dimensions match up, and I'm going to get 396.3 seconds, which you add the 30 seconds there, so the total time is going to be 396.3 seconds plus 30 seconds, which equals 426.3 seconds. That's the time it takes for that ship to sink all the way from the top down to the bottom of where it came to rest at 4,111 meters below the surface. And with that, we are done with question number 2.